Hello and welcome to this video about determinant proofs. In this video we'll prove that all of these three statements are equivalent, and if one of them is true then all of them are true. If we can prove that only two pairs are true, then the third pair will be true because of transitivity. So we'll start with the last pair. We've got to prove that the last two statements are equivalent. We know that if A is invertible, then it's row equivalent to the identity matrix. We know this from a past theorem. We can write this more compactly using mathematical symbols. We'll use the tilde symbol for row equivalence, and this is the theorem that we're using. So I've got to show that the columns of A are linearly independent. We can just write this out as Li. So we'll assume that A is row equivalent to the identity matrix. We can write matrix A out in column vector notation, using long lines to show how these column vectors occupy the columns of the matrix. And we've got to solve this equation to eventually show that the columns are linearly independent. So we know that the inverse of A exists because it's given in statement C of the statement of this proof. So we can multiply both sides of this equation on the left by this matrix, which will give us this equation that says that this vector must be the zero vector. So I'll just scroll everything up and over to the left. So from this last equation that we've solved, we know that the zero vector is the only solution for vector v, and it can't be anything else. We'll set v to have all of these entries. We'll write out this equation in column vector and entry notation. We can split the columns up like this so that the entries of vector v are in front of each of them. We can write these column vectors without the column lines and without the matrix boundary lines so that it's an equation with vectors all on one line. So we know from before that the only solution for the scalars v1 to vn is 0 because we've calculated it before. We've calculated vector v to be the zero vector, so that all of its entries v1 to vn are 0. I'll just move everything over to the left. So because of this we can say that the column vectors c1 to cn are linearly independent, because only the zero constants solve this vector equation. So I'll just summarise what I've written. If A is invertible, then A is row equivalent to the identity matrix. And so the column vectors of A, which are c1 to cn, are linearly independent. So the column vectors of A are linearly independent. I'm not confident that we can run this part of the proof in reverse. So I'll show that if A isn't row equivalent to the identity matrix, then its column vectors aren't linearly independent. And we can say that they are linearly dependent because they can't be anything else than these two things. So I'll start with A not being row equivalent to the identity matrix. We'll solve this equation so as to find the coefficients of the column vectors of A. We can then apply a lot of row operation matrices to both sides to get this equation. We'll get the reduced row echelon form of A, which should give the same solution set for V as for the above equation. And this matrix isn't the identity matrix. This matrix will contain a collection of pivot and free variable columns. And the existence of free variable columns implies that it has an infinite number of solutions. So there must exist a non-all-zero solution for these constants that satisfy the equation at the bottom of the screen. And thus we can say that the column vectors of A, which are c1 to cn, are linearly dependent. So we've been able to show this part of the theorem true in both directions for columns. Now we have to show this property true for the rows of matrix A. It'll be a similar proof for the columns, but with small scattered differences. We'll start with A being row equivalent to the identity matrix. We can write the matrix A out in row vector notation, showing how the vectors occupy the rows of A. If we get the transpose of A, then these vectors will be column vectors like before, and we can do the same thing using the transpose of A to show that these row vectors of A are linearly independent. We'll solve this equation, which is similar to the one we used in the proof for the columns of A. We know that the inverse of the transpose of A exists from a past lemma, because A is invertible. We can multiply this matrix on the left of both sides, and we'll end up with this equation. And then we can emphasize that the 0 vector is the only solution for the vector v. We'll set the vector v to have these entries. And so the only solution for this equation is for all of the entries of v to be 0. So I'll just shift everything over to the left. So this proves that these vectors are linearly independent. And these are the column vectors of A transpose. So this proves that the rows of A are linearly independent. So I'm not confident again that I can run this part of the proof in reverse. So I'll show that the rows of A aren't linearly independent if A isn't row equivalent to the identity matrix. We'll have to solve this equation again. And we can get the reduced row echelon form of the transpose of A, which will give us this equation, which will give us the same solution set for vector v. And this matrix isn't the identity matrix. So it contains a mixture of pivot and free variable columns. And the existence of free variable columns implies that V has an infinite number of solutions. So now we can say that there's a solution to this vector equation so that all of these constants v1 to vn don't all have to be 0 all at once. So we can say that these vectors are linearly dependent, which are the row vectors of A, which proves that parts B and C of this theorem are equivalent. So now to show that statements A and C are equivalent. So if A is invertible, then by a past theorem it must be row equivalent to the identity matrix. There's a sequence of row operation matrices that multiply by I to give A like this. So the determinant of the identity matrix is 1. I'll just assume it for now. We can slowly construct A from I using these row operations. I'll just scroll everything up the screen to make more room. So every time a row operation is applied to the matrix on the right to transform it into matrix A, the determinant is multiplied by a non-zero number. Applying the row swap operation multiplies the determinant by -1. Applying the row mul operation, which multiplies a row of a matrix by a non-zero number, also multiplies the determinant by this same non-zero number. This number is also not equal to 1, but it's important that it's a non-zero number. And the row add operation, which adds a multiple of one row to another different row, leaves the determinant unchanged, or it multiplies it by 1, which is the same thing. So I'll just scroll the screen up again to make some more room. This determinant keeps getting multiplied by non-zero numbers each time a row operation is applied. So because it started off at 1 with the identity matrix, it will never become 0. So the determinant of A is non-zero if it's invertible. So this part of the proof isn't reversible. So I'll have to show that the determinant of a matrix that isn't invertible is 0. We can say that it's not similar to the identity matrix. So it's similar to its reduced row echelon form. And its reduced row echelon form isn't the identity matrix I. And its determinant is 0, because it contains at least one row of zeros. And we could reconstruct A from its reduced row echelon form by applying a sequence of row operations to it. And these multiply the determinant by a non-zero number each time they're applied, which causes the determinant to remain 0. It could become non-zero if a number were added to the determinant or a cosine function were applied to it, but in this case it's only being multiplied by non-zero numbers. So the determinant of A is 0 in this case. Now we've proven that statement A is equivalent to C, and so A is automatically equivalent to B because of transitivity. So that's it, we've proven this theorem. So I hope that you've found this video to be helpful and educational. It might be necessary to watch it more than once for it to sink in. Please click like and subscribe if you liked it. Feel free to write anything helpful in the comments and to share this video, and thanks a lot for watching.